Hello everyone, I'm Anandian, pursuing engineering in Sri Venkateswara College of Engineering, and today's topic is superconductivity of materials in field of quantum computing. Firstly, what is superconductivity? Superconductivity is a phenomena in which certain materials exhibit zero electrical resistance and the expulsion of magnetic fields when cooled below a critical temperature. In the context of quantum computing, superconducting materials are used to build qubits, which are the fundamental units of quantum information. In a superconducting qubit, the superconducting state is manipulated to represent quantum information. What is superconducting materials? Superconducting materials are characterized by the ability to conduct electrical with zero resistance when cooled below a critical temperature. Superconducting materials play a crucial role in the development of superconducting qubits, a leading approach in quantum computing. In quantum computing, information is stored and processed using quantum bits or qubits. Superconducting qubits leverage the principle of superconductivity to create and manipulate quantum states. Now, these are the four brief overview of how superconductivity is employed in context of quantum computing. The first step is zero electrical resistance and Josephson's junction qubit. Third one is manipulation and readout. Fourth one is cryogenic temperature. First one, the superconductors exhibit zero electrical resistance below a critical temperature. This property allows superconducting circuits to maintain a persistent current without any loss of energy. In the context of quantum computing, superconducting loops and Josephson junctions are used to create qubits. These qubits can exist in a superposition of states, allowing for quantum parallelism. Now, the second step is one of the fundamental building blocks is superconducting quantum circuits is Josephson junction. This is a device consisting of two superconducting materials separated by a thin insulating barrier. The Josephson junction allows the flow of supercurrent, and the quantum state is encoded in the phase difference across the junction. Third one, manipulation and readout. Superconducting qubits are manipulated using microwave pulses. These pulses can be used to change the quantum state of the qubit. Readout is typically achieved by measuring changes in the resonance frequency and superconducting circuits. The state of qubit affects the resonance frequency, allowing the determination of qubit's quantum state. Cryogenic temperatures. The conductivity in many materials occurs at very low temperature, often absolutely zero, or it's in negative also. Quantum computers using superconducting qubits are typically operated at temperatures below the critical temperature of the conducting materials. Critical temperature is like below Kelvin, 273 Kelvin, that is below 0 degrees Celsius. Cryogenic cooling systems are employed to maintain these low temperatures, which is a technical challenge in the development and operation of superconducting quantum computers. There are two types of superconductors. The first one is type 1 superconductor and type 2 superconductors. Now, firstly, moving on to first type 1 superconductors. These materials become superconducting at relatively higher temperature, but they are typically excluded from many practical applications due to their sensitivity to magnetic field and Misner's effect. In this, the higher temperature doesn't mean that above critical temperature. It means like relatively above, like in minus only, relatively like greater than type 2 superconductors. The examples of type 1 superconductors are mercury, lead, niobium. Now moving on to type 2 superconductors. Type 2 superconductors can tolerate higher magnetic field and are more commonly used in practical applications, including superconducting magnets for magnetic resonance imaging, MRI, and particle accelerators. The examples for type 2 superconductors are niobium tin, niobium titanium, yttrium barium, copper oxide. Now, the conclusion. In conclusion, the integration of superconducting materials into the field of quantum computing has opened up exciting possibilities and challenges. The superconductivity, characterized by zero electrical resistance and the expulsion of magnetic fields below a critical temperature, serves as a foundation principle for the development of superconducting qubits. These qubits, typically based on Josephson junction and superconducting circuits, form the building block of quantum processes. Thank you, and thank you for visiting my channel.